Hi everyone, my name is Yong Deng, and I'm a postdoc research associate working with Professor Shanmin Shi at Washington State University. And the topic of my presentation is the predictive models for asphalt pavement rutting in Idaho, neural networks coupled with particle swarm optimization. And in this presentation, this is the outline of my presentation. I will briefly introduce the motivations and objective, and the model construction, and finally the summary. Okay, so this is a brief introduction of three major models for the pavement performance. So the first type is the empirical model. Actually, it's a regression function connecting the pavement performance and the surface conditions of the pavement. And its advantages are the simplicity and the ease of implementation, because the regression functions have explicit form, and actually its form is very simple and convenient to be implemented into the PMS. But its disadvantage is low accuracy. And the second model type is the mechanical model. The mechanical model are typically the material or structure, fracture and fatigue models. The advantage of this model is the solid foundation, because it applies the material and structure theoretical models. But its disadvantages is complicated and time-consuming, especially for asphalt pavement. Those theories are typically like the viscoelasticity, plasticity, and the viscofracture, and it depends on the time. So it's very complicated to be applied for field pavement. And the third type is the machine learning model. Actually, it's data-driven models such as the network decision trees and something like that. And its advantages is its high accuracy, because the networks and decision trees can have very complex structures, and the connections between the component of those models can be used to express the complicated relationship between the input and output. So when the model structures is too complicated, it has implicit form, so it's very difficult to be applied directly. So this is the relationship between the predictive models for pavement performance. The three major types, empirical models, mechanical models, and the machine learning models are sometimes they cannot be used solely for the performance predictions. So the researchers combined several of them for better performance. For example, this is an example of the mechanistic empirical model, which is the ME model. So it combines the empirical models and the mechanical models, and it introduced the material failure criterion and or pavement responses into the empirical models to improve the accuracy and increase the complexity of the model. And this is the typical flow of the pavement performance predictions. First, it needs the factors in 4 categories: traffic, climate, material properties, and pavement structure. And the next step is insert these factors into the pavement responses models or pavement distress models. And finally, it will output the pavement performance predictions. And this is a commercial software, asphalt pavement ME design. So back to this plot. In this study, we intended to combine other 2 types of models, the empirical models and the machine learning models, thanks to the faster developing computer algorithms. So we can change the model structure and the model calibration algorithms of the empirical models using the machine learning algorithms. So the complexity and accuracy of the empirical model will be improved. Okay, this one is the 3 parts of the model constructions. First, I will introduce the input variable selection. The second, I will introduce the model form and the calibration algorithm. Finally, I will introduce the model performance evaluation. Similarly, the input variables were used for this study also from 4 categories: traffic, climate, material, and structure. And for the traffic, material, and structure, for a better comparison with ME models, we extracted these factors from a local calibration project of Idaho State. But for the climate factors, we use the LTP database to collect climate conditions of the pavement, such as the precipitation, evaporation, and the cloud cover and the radiation. Next, since we collect these factors as the model input, especially for the material and the climate categories, we have so many variables. So the first step of the model construction is to develop a model selection, a variable selection for the model construction. First, we apply the PCA, which is principal component analysis, to describe the data domain using principal components. So we can see this is the PCA for the material categories. So we have 1, 2, 3. So we have these 6 variables, original variables for the materials. And we can say if we reconstruct the data domain using principal components, the first 3 principal components can describe the data variances, which is smaller than the original data amount. Next, we collect the principal component and original variables. We calculated the absolute correlations between the principal components and the original variables. So based on this graph, we can see the relative importance of regional variables. So the next step is to use the correlation analysis to see the correlations between the original variables. We can see at the right corner, so we can see the GSE, GSB, and the GMB have high correlations. So if we selected these 3 variables, it's not necessary. So we can just select one of them. So this is the variable selection method combining the PCA and the CA we proposed in this study. So finally, the 19 original variables reduced to 10 after this variable selection method. So this is the material structure, the model structures we used in this study is ANN, which is artificial neural network with one single layer, with single hidden layer. The reason we selected this as our model is that it has the simplest modern form of all NNs. So it has the relatively simple explicit form to connect inputs and outputs. So the first graph is the structure and the second graph is the model form. And this is the mechanism of PSO. PSO is which is particle swarm optimization, which is an AI artificial intelligence algorithm to calibrate the model. So the first graph shows the mechanism of particle swarm optimization. So each potential solution is simulated as an individual particle. So this particle has its original directions to move, but after communicating with the global and local best positions of the particles, it updates its directions to the new positions. So it's the mechanism of the particle updating its location to the desirable ones. And the equations below are the mathematical forms of PSO. We use this AI algorithm to calibrate the weight and biases of the neurons in the NN we used in this study. And this is the model construction process. We tried 4 different hidden neurons to see the updating performance of PSO. We can see all these cases with the increase of the iteration numbers, the accuracy of the model will increase. So it means the PSO algorithms worked well in this study. And we also found in this plot that with the increase of the hidden neurons, the effect of the hidden neuron numbers on the final accuracy is very limited, like this point. So we did a Welch-T test at the accuracy after 10,000 iterations to see if significant difference exists between the accuracies in different cases. And the Welch-T test tells us that the cases with 10 and 20 hidden neurons have similar accuracies after 10,000 times. So it tells us that keep increasing the hidden neurons is not necessary because it has limited effect on the final accuracy. On the other side, if we're increasing the hidden neurons, the number of parameters to be calibrated in this study will be increased as well. So yeah, we can just, so compared with 20 hidden neurons, we can just use 10 hidden neurons to have as desirable accuracies as 20 hidden neurons. Okay, so next, in addition to the model accuracy, we proposed several other, we used several other indicators to evaluate the model we built. The first one is the reproducibility, reproducibility, and it's the stability of the model constructions. So we use the cosine similarity of outputs via repetitive model construction to see if we can get similar output via the repetitive runs. And the second one is the robustness of the model, and is the performance of constructed models on outliers. So we use the validation data set, which is new to the model. So we check the model accuracy to see if the constructed model is desirable as well to the new data set. And the third one is the sensitivity. Its definition is the relative change in the response of model outputs corresponding to a small change in the model inputs. So we obtain the relative sensitivity of the input and output development to see if the constructed model can predict it reasonable, can give us reasonable predictions. So the first one is the reproducibility. We calculated the cosine similarity of model output with different accuracy and hidden neuron numbers. And we can see the first trend is that with fixed hidden neuron number, if we increase the model accuracy, we can see the mean value of the similarity increase and the variation of the similarity decrease. So it means the model accuracy has positive effect on the similarity, which is the reproducibility of the model. And the second pattern is that if we fix the model accuracy and increase the hidden neuron number, we can see the mean value of the similarity increase and then decrease, and the variation of the similarity decrease and increase. So we can see that if we keep increasing the hidden neuron numbers, finally it will have negative effect on the similarity of the model output, which is it has negative effect on the reproducibility of the model. And it shows it may exist optimum hidden neuron numbers to be selected for the model construction. And the second one is the robustness of models. And we output the validation accuracy versus the training accuracy and the hidden neuron numbers. We can see if the accuracy of the constructed models is higher enough, which means it's higher than 0.9, the validation accuracy is desirable as well. And also we conducted the Shapiro-Wilk test to check to check if the residuals of the validation of the predictions for the validation dataset follows a normal distribution, and the test result tells us that most of the most of the construction models in repetitive constructions has desirable robustness. And the last one is the sensitivity. First, we output the relative sensitivity of the model inputs. This is the rank of all the used variables for the model construction. We can see the traffic variable ADDT and the environmental factor freeze-thaw days has the higher effect on the rot depth development. Also, we can see where these selected variables have comparable effect on the final rot depth development. So it means the variable selection method worked well in this study. And the second graph shows the development curve of the rotting with two major factors, ADDT and the freeze-thaw days. We can see with the increase of the ADDT, the rot depth increased as well, which is a general acknowledgement. And oppositely, with the increase of the freeze-thaw days, the rot depth will decrease. So it tells us the freeze-thaw days shows the degree of the oxidation aging of the asphalt layer. So with the increase of the aging degrees, the layer will be hardened, so the rot depth will decrease. And this is the comparison of
you have 2 minutes, okay?
Okay, okay, I'll wrap up soon. So this is the comparison of our models with the traditional ME models. This figure shows we have better accuracy compared with the traditional ME models. Okay, this is a summary. The highlights of this study, the first one is we propose a 3-step variable selection method using PCA and CA, and it worked well to select and reduce the dimensionality of the original data domain. The original data dimensionality. And the second highlight is the model evaluation method with accuracy, reproducibility, robustness, and sensitivity. So we not only the accuracy, we can focus on other model properties to evaluate for the evaluation. And the findings in this study is that the hidden neural numbers have complicated effect on the model performance. And we cannot just keep increasing the hidden neural numbers for the higher accuracy because it may have negative effect on other model properties. And the second finding is that there is a relationship between the model accuracy, reproducibility, and the hidden neural numbers. So it tells us it may exist an optimum number of hidden neurons. So in the next time we construct the AN, we can do the similar procedures to comprehensively evaluate the model properties with different hidden neuron numbers to see if if we can get a most desirable one. Okay, this is the disclaimer of this study, and the one of the funding agency, Idaho Transportation Department, claimed that this research project is it reflects the reviews of the authors, which are me and Professor Shi, and who are responsible for the facts and accuracy of the data presented here, because the result presented here does not constitute a standard specification and regulation currently, and has not been accepted for the final report. Okay, and this is the email address of Professor Shi and me. So if you have any questions, feel free to contact us via these email addresses. And the details of this study is included in a paper under review.